Welcome to the Matrix Seminar Series. It's our pleasure today to welcome Dr. Murtuza Jadliwala, who is an assistant professor in the Department of Computer Science here at UTSA. In addition, he's also a research thrust lead within Matrix, so we're very happy and excited to hear about his research. Currently, he's the director of the Security, Privacy, Trust, and Ethics in Computing Research Lab, or the SPRITE Lab at UTSA. He obtained his PhD degree in Research Fellow at the Swiss Federal Institute of Technology and an assistant professor in electrical engineering and computer science department at Wichita State University. He was selected as an AFOSR Summer Faculty Fellow in 2015. He received the Duane and Velma Wallace Excellence in Teaching Award in 2017 and received the National Science Foundation's Career Award in 2020. Dr. Jadliwala, thank you very much for presenting. Go ahead.
Thank you very much, Henry, for a kind introduction, and good morning, everyone. Let me begin by first thanking Henry and Divisha. Unfortunately, Divisha couldn't be here, but thank you to them for hosting this Friday seminar series regularly. They are very interesting. And also thanks a lot for inviting me and giving me an opportunity to talk on this forum and to kind of present my research. And thank you all for basically taking time out of your busy schedules to come to my talk. So the title of my talk today is Friend or Foe, ML Meets Privacy. So far, speakers in this seminar series, at least the ones that I've attended, have talked about how machine learning can be used to solve problems and to design new applications for general societal good. And I'm going to take a slightly different route over here today. And I'm going to talk about how machine learning can be used for achieving nefarious objectives or malicious objectives. Right? So before I begin, let me start by just giving a brief outline of my current research focus. My current research interest is basically in almost all aspects of security and privacy. Some of my current research projects they fall into the areas of mobile, IoT, software, and distributed systems security and privacy. In order to solve problems in this domain, I often use machine learning tools and techniques, game theory, graph theory and combinatorics, and applied cryptography techniques. Majority of my projects involve a significant system design, development, and validation component as well. And you will see that some of those system design and development in this talk today. I've basically in these broad areas, I have currently working in several more individual projects. Several of these are funded by National Science Foundation and other agencies. And today I want to talk about our work and I present some results on our research in mobile and wearable security and privacy. And the primary reason for doing that is because we have been working on that for the last several years now. We have a lot of results. Obviously, I'm going to just give you a very bird's eye view of what we have done so far, and maybe just a few projects. But that is an area that is very near and dear to my heart. So I will talk about it today. So before I begin, I need a volunteer, and before you sign up for volunteering, please listen to what the volunteer needs to do. The volunteer needs to send me a chat message with the following information. Full legal name, social security number, banking password, and a 4-digit ATM card PIN that you use. Anyone interested in volunteering? All right. I see a couple of them, but anyways, the moral of the story is that most people, right, do not like to provide their personal information to untrusted entities, including myself, right? However, there are always malicious entities who are after your personal information. And how do they try getting this information? Typically, lots of techniques, visual eavesdropping, social engineering, also taking advantage of weaknesses or vulnerabilities in technologies that we use every day, right? And so today in this talk, we'll talk about one such weakness in technology. And the technology that I want to talk about is wrist wearables, right? Or also smartwatches or fitness bands, right? So smartwatches, fitness bands have basically, become an almost ubiquitous consumer technology. Almost everyone is aware of them. They extend the functionality of your traditional wristwatches beyond just simply timekeeping, and they do that by capturing rich contextual information about the user, about the wearer, and based on that information, they enable several context-based applications, right? Things like fitness monitoring, health monitoring, navigation, so on and so forth. Right? So how do they how do they achieve this? How do they enable these applications? And this is by means of a broad variety of onboard sensors, right? Typically on most wearable and mobile devices, you would see two types of sensors: the front-end sensors like microphones, GPS, cameras, which users can directly interact with. And the second type of sensors are back-end sensors, which we refer to as back-end sensors, things like accelerometers, gyroscopes, ambient light sensors, temperature sensors, which are very important to applications. However, users don't really directly interact. Um, in this work, we are focused on a very particular type of sensor, which we refer to as a motion sensor. And there are two types of motion sensors: an accelerometer, which typically records the device's acceleration, right? So rate of change of speed, and a gyroscope, which basically records the device's angular rotation, right? So angular rate of change of speed. And motion sensors are very important to mobile applications, primarily because of the nature of these devices. They're mobile. It helps applications to adjust to the mobile environment, right? So if you have your phone and if you turn your phone sideways, your application also kind of turns around, and that is enabled by means of motion sensors, right? And because of this importance of motion sensors to applications, these motion sensors typically have all applications have typically default access to these motion sensors, right? So basically, they don't really need to, when you install an application, you don't really need to explicitly give it specific user permissions to access these motion sensors, right? And sometimes we refer to these sensors as also zero permission sensors, and this is found in most wearable OSs such as Android and iOS. Right. More importantly, applications cannot also manually turn off motion sensors. Right. So if you ever looked at your Android phone, you don't really have or don't really see a way to kind of shut off an application's access to motion sensors. There has been some progress on access control to motion sensors recently, and I won't talk about that. But some of most of this work was done in an era when actually really there was no such access. Okay, so the bigger question that we need to answer is, can an adversary take advantage of motion sensor data from a wrist wearable to infer private information inputted by the user's device wearing hand, right? So that's basically effectively what we'll talk about today in this talk. And so the types of interfaces that we care about are basically divided into two types, right? So we have human-computer interfaces and human-machine interfaces. Human-computer interfaces are interfaces which are connected to a computer or a computer system, right? The type of attacks that we'll discuss today are things like keystroke inference. And why these attacks are relevant? Because obviously, if your keystrokes are kind of inferable on these interfaces, they could basically result in a loss of security and privacy in the cyber world, right? And then the second type of interfaces we'll be talking about are human-machine interfaces, right? These are interfaces typically present on physical machines, right? Not computer systems. Things like log dials, etc. And what we'll be talking about today is how can we infer a user's input on things like combination logs and obviously inferring these the ability to infer these inputs could result in a loss of security and privacy in the physical world, right? Okay, so before we so let's get started. So my goal is to at least give you some details about the part one of my talk, which basically is focused on inferring private user input on human-computer interfaces, and we'll talk about two scenarios: inferring keystrokes on a smartphone touchpad and inferring keystrokes on an external keyboard. And then, if I have time, obviously I'll go about the second part of my talk and conclude. Okay, so let's go with the first scenario, right? So in this scenario, the scenario is straightforward. You have a basically user who's wearing a smartwatch and holding a smartphone in the wrist, and typing or tapping on the touchpad or the keyboard of the smartphone. And the goal over here is to answer the question: is it possible to infer what is being typed on the phone based on, or solely based on, the wrist movements, right, observable by the smartwatch's motion sensors? Now, the main idea over here is when we basically did some initial experimentation, so we saw that whenever users tap on their touchpads, right, or the smartphone keyboards, there's a discernible motion which is captured by the smartwatch's accelerometer, right, specifically the linear accelerometer. And we thought that we could use that discernible reading to infer what is being typed. And then we did a little bit more further investigation. And again, here we are focused on a touchpad or a keypad, which is purely numeric, as you see, right? So we're trying to infer numbers that are being tapped. So some additional investigation led us to see that basically tap on each number of the keypad produces a very characteristically unique motion of the wrist. And thus you see a very characteristically unique motion pattern on the accelerometer. So that is first observation. And the second observation is we saw that this is kind of fairly consistent, right? Not only basically across the same user, but also across different users. And so we decided to kind of use that in our investigation further, right? So our attack setup is straightforward. We have an adversary who somehow gets remotely access to the victim's smartwatch motion sensors. And as I described and talked about before, because applications typically don't have any restrictions on accessing these sensors, any application can effectively access these sensors, right? So the adversary can either fool the user into installing some form of a Trojan horse, or basically even a well-known or a trusted application can effectively carry out this attack, right? And so once the adversary has collected such motion data, he's going to execute the keystroke inference attack in an offline fashion, right, after the fact. So the first attack that I talk about it focuses on two holding styles, and I call them same hand holding, where basically the touchpad and the wristwatch are basically held in the same hand. In the first scenario A, if you see, the typing actually happens with the non-watch wearing hand, and in the second scenario B, you see the typing happens with the watch wearing hand. And again, the reason we chose these two scenarios, which are because these were the two most popular scenarios that we saw that users were typing or tapping with. And so our basically framework was pretty straightforward. It's based on the observations that we kind of talked about before. I'm not going to go into details of all these individual modules, but effectively we had a key presence detection module which detected when a user pressed a keystroke, and then we basically did a lot of data cleaning. We did feature extraction. We used both time and frequency-based features, and then we basically trained a bunch of machine learning tools or machine learning techniques, basically using data collected from a set of participants. The kind of techniques we use were both parametric and non-parametric learning techniques, and actually we use a kind of an ensemble strategy, right, to basically to get our results. And so once these models were trained, we obviously used them to attack and basically to classify. And so effectively our classifier was a multi-class classifier, right? And we use that to predict the keys. So that was the first attack. The second attack, we focused on a slightly different holding style. This was basically called different hand holding, where the touchpad or the smartphone was in a different hand than the wristwatch, and the user typed with the wristwatch wearing hand, with the smartwatch wearing hand. Right. Over here, actually, there was a little bit of a. If you see. Over here, the motion signatures are going to be a little bit different. They're not going to be basically capturing the tap itself, but effectively they're capturing the linear motion of the hand, right? And so the earlier framework is not going to be useful over here. And so effectively in this scenario, what we do is we design a slightly different framework where we don't classify the number being tapped or typed. Rather, we classify the direction of the movement of the hand, right? So whether it's going north, south, east, west, So we had 8 cardinal directions, and we basically effectively were trying to just classify the hand movement. And based on that classification, we then basically ran a tracing algorithm, right? Which was effectively giving us a list of potential numbers that could have been typed, right? So that's basically effectively the idea in this framework. Then we basically did a bunch of experiments. We basically used, and again, this is just for one of the experiments, and I'm going to talk about just one, but we did a lot of them. So for one of the first experiments, we basically collected, we used a Samsung Gear Live smartwatch, a Moto XT1028 smartphone as basically the target phone. And obviously we used the linear accelerometer on the smartwatch and the phone, which was sampled at 50 hertz. And this was a keypad that we use, which is a pretty standard numeric keypad on these phones. The first experiment basically involved 12 participants between 19 and 32 years of age. They basically entered 300 keystrokes, 30 per numeric key, and basically each participant entered 300 keystrokes. And the evaluation strategy involved basically 1-versus-1 testing, where basically the training was done, the training and testing was done with the data from the same user. A 1-versus-all scenario where the training and testing was done, when the training was done from every other user and the testing was done on a target user, and then a kind of an all-versus-all scenario. So we kind of mixed up data from all the users and then selected a portion of it for training and then a portion of it for testing. I think we used a 60-40 split for that. And as I said before, we basically use time and frequency domain features. I'm not going to go into details of which exact features that we use. All those details can be found in the paper that I'll shortly list. And then we use the Weka libraries. At that time, Weka was one of the very popular machine learning implementation libraries. This is, I'm talking about 2017. And we basically implemented, as I said, 5 different machine learning models. The simple linear regression, random forest, k-nearest neighbor, SVMs, and binary decision trees in an ensemble strategy. And then, as I said, we did some additional experiments where we basically evaluated a more uncontrolled typing scenario. So the previous experiment was done in a lab. We basically also did experiments with different smartwatch hardwares, also testing with one and training with one and testing with another one. We basically also did some additional experiments on using a QWERTY keyboard, right? So initial experiments focused on a numeric keyboard, but the later ones focused on a QWERTY keyboard. So just to kind of give you some idea of the results. So if you look at some of the results for both the typing styles A and B, we observed that the attack using the smartwatch resulted in fairly good accuracy. We were able to get as high as 95% accuracy, but overall, I think our accuracy, hovered around 80 to 85%. And this is in the 1-versus-1 scenario. Obviously, this is a very, I would say, impractical scenario. Generally, you would not have training data from the target. So the 1-versus-rest scenario is actually a little bit more practical scenario. And even that, I think we were able to get kind of fairly decent accuracy for the first attack using basically our framework. For the second one, also we got pretty reasonably good results. I think that was a little bit more tougher framework to design. For our directional classifiers, we were able to get close to 90% accuracy, accurately classifying the cardinal directions. And in the end, basically, obviously, this particular framework, this framework, the second framework, really did not classify individual tabs, but rather basically, gave a list of potential numbers that were being typed. So in this case, out of the 240 test numbers that we used, almost 85 were basically unambiguously identified, right? But I think that, this is basically, so the accuracy is kind of 43%, but effectively you got numbers which were kind of, pretty close or in some sense neighboring to the target type number. So I think I will kind of conclude that first scenario that I explained with basically the following. The experiment results from our smartwatch motion sensor-based inference framework for inferring key taps on numeric touchpads was that basically, it was a very effective framework. We saw that there, such kind of attacks could be feasible, and basically, some of the additional details, and there are a lot of additional details which I've just skimmed through, could be found in some of our related publications, which I list over here. Okay, so that was the first scenario. Let's go on to the next scenario. How do you infer keystrokes in external keyboards, right? So basically, as the scenario says, basically, if you have a user who is typing on an external QWERTY keyboard, like something like you see with a smartwatch on one of the hands, is it possible to infer what is being typed on this keyboard, right? Just using the wrist motion data available from the smartwatch sensor, right? So the main research challenge over here was, well, there are several research challenges. First research challenge, obviously, if you see, we just had partial data, right? So basically, only those keystrokes which were done with the watch wearing hand were discernible with basically using the motion data available from the watch, whereas the other the keystrokes typed with the other hand were not that easily discernible, right? So we were getting some readings, but obviously they were not enough to basically to identify which keystroke was typed. The second challenge is that it doesn't matter which keystroke you type, right? So if you just look at the motion sensor data corresponding to the moment where the keystroke was typed, it doesn't really give you a lot of information, right? Because effectively, it doesn't matter where you type on the keyboard, it's going to produce the same tap motion signature. So effectively, we had to really use the linear movement of the hand across the keyboard again to identify what was being typed, right? So we have two challenges. We have partial data, and basically we need to kind of use the linear motion of the hand, right? So our framework was very similar to the previous attack scenario, the second attack that I explained in the previous scenario, right? So what we did was we did some research, and we found that most users were proficient in typing. Obviously, with the left hand, they're going to type on the left part of the keyboard, and the right hand, they're going to type with the right part of the keyboard. So for the first thing that we did is we separated the keyboard with this virtual or this imaginary line, right? So we basically separated it, partitioned it into these left hand set of keys, which we always assume that are going to be typed with the left hand, and the right hand part of the keyboard, which we'll assume that is going to be typed with the right hand, right? So the idea over here is we use this kind of partition to determine that whether the target user typed with the left hand or with the right hand, right? So that was the first thing. The second thing we did was we basically, again, like the second attack in the previous scenario, we will try to basically identify based on the linear movement of the hand, which cardinal direction the hand is moving, right? So whether it was moving north, east, south, west, and so on, right? And so basically, based on these two observations, we can see, we can basically create a table like this, right, of which potential letters could be typed with the left hand, which potential letters could be typed with the right hand, and then which pairs of letters could be typed for each movement of the hand that you can observe, right? And once we basically have this setup, then effectively what we need to do is as follows, right? So the next thing that we do is that we basically create a very huge dictionary, right? Maybe 60,000+ words. And we basically create a word profile for each word in the dictionary. And the word profile looks like this, right? So we separate out the word into pairs. And for each pair, we are going to basically create a word profile depending upon whether the individual letter in that pair is on the left-hand side or right-hand side. And if you want to go from the first letter to the second letter, what kind of movement you will see, right? Whether you're going to see a north, south, east, west, so on and so forth. And so basically we created such word pairs for all the words in the dictionary. And so now basically we had our setup ready, right? So effectively what we needed to do now is we needed to train a machine learning model, which was able to classify two things, right? So we trained two models, right? First, whether the user typed with the left hand or with the right hand, right? So that means that the keystroke that was observed was with the left hand or with the right hand. That was the first classifier. And then the second classifier effectively classified the cardinal direction of the watch wearing hand, right? And then we use the output of both these classifiers. So obviously we trained both these classifiers using data that was available from a set of participants. And then basically in order to carry out the attack, we basically use the outputs of these classifiers to generate the word profile of the word that is currently being typed by the target user, and then match it to a dictionary that we have already created, right? And basically, voila, that basically will give us, in some sense, what word was being typed. Now, there are several issues over here, and I will talk about some of them. One of the issues is that um, there are many words in the dictionary which obviously will have the same word profile. And so obviously in that scenario, what we did is we ranked such kind of word lists which have the same word profile based on how frequently these words appear in English conversation, right? And so obviously, effectively, this framework is not going to always give you the target word that the user typed, but a word which actually effectively has the same word profile. So it kind of reduces your search space a little bit. Okay, so for our evaluation, we basically collected data from 25 participants. This was the hardware that we use for implementing our machine learning libraries, which was basically effectively a neural network. We used the PyBrain libraries. So we did many experiments, and I'm going to just present a very high-level overview of 3 experiments. The first experiment was basic text recovery, right? So where basically our participants typed, both for training and testing, 10 sentences in this list 6 of Howard sentences. So the reason why this list 6 of Howard sentences, because it contains sentences which are phonetically balanced. Effectively, there are 48 words when you combine all these sentences together, and they include all the words on the keyboard, right? Or in the or all the characters in the English language. So that's why basically we use that. And in this experiment, we effectively saw that our left-right classifier was very accurate, right? So we basically, in our experiment, we almost achieved 100% accuracy. And our directional classifier was basically just giving 5% miscalculation. And this is just one example of a potential recovered sentence. And so if you look at that, we were able to recover several words. Obviously, we were not able to recover several words, especially smaller words. And there were some words which we recovered which had the same word profile. So this is an example, right? The show word and the sums word actually had the same word profile. And so what we really, what I really wanted to say over here is that this is a good result to begin with. Now, obviously, if you kind of add more intelligence, if you kind of add word prediction, if you add language analysis, you can further improve this a lot more, right? The second experiment was basically, again, we tried a more contextual and a larger dictionary. So participants were asked to type a paragraph of 40 words from a news article that appeared in NPR on a Greece debt crisis. And basically, we created our dictionary using 6 other articles, which were kind of similar. And one of the difference over here is that our dictionary contained only 27 words out of the 40 words that were actually typed by the participants. So our dictionary was not complete, right? Which is possible. And what we observed is, I think, obviously, some participants had pretty good, for some participants, we had pretty good word recovery, even using the contextual dictionary. So if you look at the orange lines, these are the orange bars are the one which show the accuracy or the word recovery percentages when basically all the words typed by the target user are not present in the contextual dictionary, and the yellow bars are the ones where they are present. One of the very interesting features that actually kind of comes from this observation is, so if you see this dividing or this partitioning line, this is basically the data that we use for a training. Right? So the adversary just used his own data for training, right? And these were all the data collected from all the remaining participants was just effectively used as test data, right? And what you see over here is those participants, obviously, which typed very similar in terms of speed to the adversary, right, which was us. They had very good, we had very good accuracy for them, and obviously those who didn't type as similar to the adversary, we had kind of slightly poor word recoveries. And so this really also shows, because our adversary was actually a very good typer, right? And so effectively this shows that if you are a bad typer, our framework does not work as well. But if you're a good typer, our framework works pretty well. And so I'm going to, we did some attacks with also a larger dictionary. Just for the interest of time, I'm going to just skip this right now. But I'll come back to it later on during the question and answer sessions if you have more questions on that. And so the summary of the scenario 2 was we were able to experimentally validate that smartwatch motion sensors can be used to infer keystrokes on even external QWERTY keyboards, right? So this is a possibility or a feasibility. And basically our results are available in this paper, which is available on our labs website if you want to have a look at it. Okay, so that kind of brings to the conclusion of my first part of my talk. I think I'm doing good on time, so I'm going to go on to the next part of the talk as well. And basically, what I'm going to talk about over here is how do you infer private user inputs on human-machine interface, right? And over here also, I'm going to talk about two scenarios that we consider. The first scenario is inferring unlock codes on combination locks, right? So we call this attack scenario 3, right? So let's see basically what this involves. So in this particular scenario, our target system was a combination lock, something similar to this master lock padlock. And I'm sure that most of you have kind of used a lock like this before, right? So basically, it's a small lock which is typically used in gyms. It has a basically small dial on the front, which has roughly 40 digits on the dial. The unlock combination of basically this lock typically involves 3 digits, right? A, B, and C. And basically, each of these 3 digits obviously are from 0 to 39. Roughly, if you see all these particular digits on the dial, you could imagine that theoretically there could be 40 to 3 combinations, right? Unlocking combinations or possible combinations. But in practice, because of the physical limitations of these locks, at least this specific lock, the actual number of combinations are much less. They're roughly around 4,000 valid combinations. So just before going, I want to talk about the unlocking procedure, right? So I'm sure that you have unlocked this kind of lock. So how do you unlock this lock? So this unlocking procedures, each lock has a very specific unlock procedure. And basically, let's say that your unlock combination code was 20. So you would typically start from some number, and you would turn clockwise direction, and with the first digit in your unlock combination, you will pass it twice, and then you will land on that first digit. Then you would basically go anti-clockwise, pass that second digit once, and then land on the second digit. And then you would turn clockwise once, and without passing that last digit, you would land on that last digit, right? So that's how you basically effectively unlock a combination padlock, right? And so the other target systems, there is basically a safe that we also use in our experiments, which is actually a little bit much more larger interface, where it has basically around 100 digits, and it has 4 digit combination unlock code. And effectively, my focus today is I'm going to try to focus my explanation based on the combination lock. And I think the results are kind of transferable to other target systems. And we have done experiments with other target systems. So effectively, the goal over here in this attack is straightforward. You have a user who is wearing a wrist wearable and is basically unlocking the lock. He's basically he or she is entering the combination. And the goal is to infer what that combination was, right? So it's a straightforward goal. Over here, we are going to use not the linear accelerometer, but we are going to use the gyroscope, because that is the one that is going to give us the information, because it measures angular rotation. So that is the one that is going to be useful in trying to see if we can infer that. Our adversary model is pretty similar to the previous scenarios. There are a few additional requirements. The first requirement basically that we have is that the adversary needs to have some physical access to the lock. Obviously, this is important, because if the adversary never have physical access to the lock, then there's no point guessing the combination lock. The other thing, and this is kind of an important assumption that we make, just to kind of make the scheme a little bit more manageable. You could actually try this framework without this assumption as well, but obviously you'll have to try a lot. And so the assumption that we make is the adversary is able to preset the starting position of the dial on the lock to the position that the adversary wants, right? And obviously, as before, the adversary is able to record the gyroscope data to carry out the attack. So let's basically, before I outline the framework quickly, let me see some observation. Let me talk about some observation that we use for this attack. Right? So the first observation is that the angular displacement of the wristwatch that we calculate from the gyroscope, the smartwatch's gyroscope, is not the same as the angular displacement of the lock's dial. Right? So if you see the figure at the bottom, the one with the red lines, this is actually the actual angular displacement of the log's dial in each of these three phases. Whereas on top, you see the gyroscope data that we collected from three participants, and you see that they are kind of a little bit apart, right? So they're not the same. And this is kind of, this is intuitive because obviously, this could be because of the gyroscope sampling rate and errors. This could be because that the user's wrist motion is not perfect. So obviously the dial might be moving a little bit faster than the user's wrist, and so on and so forth, right? So there can be many reasons, but this is one observation that we made. The second observation that we made was that the angular displacement of wrist calculated from the smartwatch's gyroscope is a linear function or linearly increasing function of the transitions on the log's dial, right? So this gives us some direction on how we can attack this, right? And one of the other things, important things that we saw is that across the three participants, we saw that this relationship is fairly consistent and it is homologous, right? So this is where we thought that we could employ machine learning to maybe create such an attack framework, and that is what we did, right? So if you see over here, this is how our our inference framework looks like. We basically first designed a segmentation, an activity detection and segmentation algorithm. So the detection algorithm will detect when the user is actually unlocking the combination lock, and the segmentation algorithm will segment data corresponding to each phase of the unlocking process, right? And then basically, we obviously collected certain features in the training phase and basically labeled them, and then use it to train a linear function using least square fitting. And our linear function that we learned was basically something like this, right? Effectively, it's a function between the number of transitions that are actually made on the log's dial with respect to the angular rotation of the user's wrist, right, which is captured from the gyroscope data. And once this function is learned, effectively you can use this learned function to basically infer the number of transitions on the log using just the gyroscope data. And once you have the number of transitions on the log, you can easily map it to the combination code, right? And so basically, that's not completely the framework. Obviously, one of the things that we observed when we had such a deterministic framework was that obviously because of the errors in the learning process, in the inference process, the obtained code was not exactly always the target code, right? And so effectively, what we did we also basically learned a Gaussian distribution, and we observed that basically the numbers which are surrounding the numbers which this framework obtains are also likely to be the part of the target combination. And so effectively, if the framework that I just described gives you an output of 33,716, that could be one feasible output, but that may not be the actual final code, and you may have to try other combinations which are closer to it as well, right? So for example, in this case, 33,715 is the next combination you would try, and 33,717 would be the next combination you try. So effectively, our framework does not really output one single combination. It gives you a small list of potential combinations, and you basically try them in that order, right? What we do is we reduce the search space from a large number of potential combinations to a very small set of feasible combinations. And again, we basically carried out several experiments. I'm going to basically skip some of these details. What I want to talk about is this plot in the middle, if you see the B and E. And actually, this is the plot where we basically tested for the 4,000 valid padlock combinations. And we observed that out of the 4,000 combinations, 235 of those combinations were always getting detected in the top 10, right? So we were basically able to predict those successfully when participants were typing it, when participants were entering it, right? So although the overall accuracy may seem pretty poor, there were certain combinations which were kind of much more easily predictable than others, right? And so we tried to characterize some of these combinations, and we saw effectively that combinations which had less number of transitions, right? That means they were such that the user had to move less. They were obviously much more accurately predictable or inferable than others. And so I will kind of conclude this with a quick summary that, so in this work we were able to show that it is possible to design an attack framework which can detect mechanical lock combinations from smartwatches gyroscope data. And we also demonstrated the efficacy of that in both controlled and realistic settings. And I didn't talk about the realistic setting over here, but we did some work where we asked the participants to take the lock home and just enter a secret combination, and we were able to kind of also infer that. And so a lot of our results are kind of appear in this publication. And basically, please feel free to have a look at it if you have more questions or concerns. And so I'm kind of coming towards the end of time, and so I'm just going to rush through the last scenario. And some of the more recent work that we did was inferring handwriting, right, from smartwatch motion data. And so I've talked about these three scenarios over here. So in this scenario, effectively what we do is we want to see if it is possible to infer what a person is writing, using a pen or a pencil, if he or she is writing it with a watch wearing hand. In the literature, we saw effectively a lot of work. So when we started working on this project, we saw that there was a lot of work in this direction, which were focusing on different writing styles. And effectively, all of them were machine learning based algorithms. One of the things that when we read those works a little bit carefully, we observed that they were making a lot of assumptions. The first assumption was some of the works use a very specialized device. Others basically targeted or focused on only specific characters, like uppercase characters. Basically, others were basically just using a very personalized setting for inference, right? That means training and testing with the same user's data. And so what we wanted to do in this work was, so we gave the idea of designing a new model, because effectively there was a lot of work over there already. And so what we instead ended up doing is we instead ended up evaluating if all these efforts in the literature did actually work, right? So did they work when you were using a consumer grade risk variable such as a commercial off-the-shelf smartwatch in a generalized setting where you don't have training data from the target user. The writing is completely uncontrolled or unconstrained, so there are no constraints on how a user writes. And basically, both uppercase and lowercase alphabets were also modeled, right? And I'm going to basically just jump to the results directly. And basically, these are some of the machine learning models that were actually used by those efforts. And one of the things that we saw is that when we replicated some of those research efforts, we saw that basically what was proposed as results by those authors in those settings didn't really stand in our scenarios, right? So if you look at this uppercase scenario, our replication showed that schemes which were claiming that they had 91% accuracy really had just 17% accuracy in our settings, which included unconstrained writing, smartwatch as a basic data collection device, and so on and so forth. And this was in a personalized setting, right? So your training and testing data is from the same user. And when you went to a generalized setting, it was even worse. You had basically schemes which were not even giving us an accuracy more than 5% or 9%, and this is kind of really bad. So effectively, we ended up summarizing from that research effort that maybe handwriting inference is not that feasible with using the current state-of-the-art smartwatch hardware, especially in a very realistic setting, right? So obviously you could achieve this in a very constrained lab setting, but maybe when you are you have a very unconstrained setting, this may be not possible. Our code and everything else could be found on this website. We also received the ACM's replicability award for this work, and basically details of my publications can be found over here, right? So I don't have time to discuss protection mechanisms. Unfortunately, I want to make sure that I kind of give you. So I'm going to skip this part of protection mechanism. I'm just going to give a brief, just a very brief summary of what we're doing right now, and then I will take questions. And so we are working on some of very interesting projects right now. One of the projects that we are working on is how do you kind of take advantage of modern smart lights to exfiltrate data out of a secure network. So this is one of the projects that just got completed. The second project that we are working on is we are trying to see if it is possible to infer keystrokes using your Zoom or video calls, right? Just using your shoulder movements, right? Or just by observing the shoulders. This is an effort which has just recently got completed. We are hoping to get a response from the conference/journal where we submitted this work very soon. But this is a really interesting effort. You'll see more about this in the coming few weeks if it gets accepted. And then the last work that we focused on is it possible to infer these kind of physical keys, right? So we talked about combination locks, right? But is it possible to infer bitings on physical keys, which are used in pin tumbler locks, right? Using again, either motion data or using audio data or even video data. And because the reason why we focus, so these works really don't focus solely on wearable devices, but they focus in general the area of IoT, right? And because there is so much data that is available in different forms, we wanted to see how it impacts users' privacy. So some final thoughts. I will end this talk with some last thoughts on my mind. We believe that sensors on modern mobile and IoT devices, if not appropriately controlled, can be a source of significant privacy threats. Hopefully, I have given a lot of examples in which it can be a threat. I've presented, we have presented some attacks and we have shown that the feasibility of some of these attacks. But again, I must mention that we have not seen any evidence of their really strong occurrence in the wild, which is a good news, right? But again, the takeaway message that I would like to give over here is that we need to be aware of the privacy implications of new technology as it permeates our lives, right? So please do that. And the last thing is machine learning will continue to play an important role in the design of such adversarial tools that we have talked about today. And this is kind of the ugly side of ML, right? So we have so far seen all the good side of ML, right? But we also need to be aware of how some of these learning tools can be misused for achieving some of the nefarious objectives. Obviously, any talk would not be complete without acknowledgement to people who made it possible. If you see this, my postdoc on India was heavily involved. He was actually my PhD student before in a lot of these and almost all these efforts. And some of the students, PhD, and some of the very fantastic undergraduate students who participated in these efforts. Also, my collaborators, both at Wichita State, Google Zurich, and AFRL also participated in some of these efforts. And obviously, this would not have been possible without funding from our funding agencies such as National Science Foundation, AFOSR, and AFRL. And I really thank them for giving us an opportunity to conduct this research. So with that, I hope I'm on time. I will stop talking and I will give other folks an opportunity to talk and ask me questions.
Thank you so much, Murtuza. That was an excellent presentation and you're right on time. So I think the last few weeks we've invited the presenters to ask the questions directly. So we'll kind of start back with some of your work on the keystroke dynamic stuff. Anurag, would you like to ask your question?
Yeah, thank you, Henry. So here I have a question. So like when you said you were like trying to basically deduce which keys were typed based on the finger movement, based on the movement of hands. So basically some of them use all their fingers. So some of them maybe use like fewer fingers or have different styles.
So which is it a scenario one you're talking about?
Yeah.
Okay, let me just go to the slide so that I have a reference to what you're talking about. Okay, let me go to, okay. Okay.
So there's a lot of variance in how people type, right? So how does the model account for this variance? And based on like, and since we are taking the readings directly from the basically IMU in the smartwatch or smart device, right? So it already has a lot of noise. So how do we account for that noise? Is there any way to do you use some kind of filtering mechanism for?
Yes, and that's a great question, and you're right. So obviously, and I did explain some of the techniques on how we go from the motion data to features. But basically, we do a lot of data cleaning, and we try to design our features such that that kind of variance is kind of removed as much as possible. Obviously, if your question is, can we completely get rid of that? Obviously, no. And that is the reason that you see the errors that you get in the outcome of the or the output of the model, right? So those kind of those are precisely the reasons why our model is not perfect, right? And we get those errors because people
Because
type.
like there's so many different kinds of keypads, there are different kinds
Sure.
of orientations in which people might hold their
Oh,
phones.
absolutely.
So like that.
Yeah.
So do you think like moving ahead, would you look forward to a method which like kind of adapts itself to how the user is typing and then based on that generates prediction?
Absolutely. And so this work that we did and the one that I presented, this framework, I would say it's kind of a little bit outdated now. It's 4 years old. Actually, there was a very recent work in a conference called UBConf, which I attended in London. And they kind of built on top of our framework to build a framework which apparently was, which kind of took care of some of those things that you're talking about, right? How do you make it participant invariant or basically, typing style invariant? But definitely, yeah.
Okay. Thank you.
Thank you for your question.
Thanks, Anwar.
Amanda, would you like to ask yours?
Absolutely, thank you. So I was kind of curious, as somebody who relies heavily on autocomplete and autocorrect, how that might be kind of effective in here. And if I realize that would kind of cause a kink maybe in some of the predictive frameworks, but maybe it would be something that could be integrated, or have you guys thought about this angle yet?
Fabulous question. No, the simple answer is no. So that question came up as well during when we're doing this work. Obviously, autocorrect effectively implies that people are going to type less, right? And the way you'll have to solve that challenge is that you'll have to use some of the same prediction frameworks that these autocorrection techniques use to basically do that, right? So let's say that you typed you were typing a 5 or 7 word, a 7-letter word, and you type 3 letters, and then the autocorrect or the whatever the mechanism that the operating system is using, gives you a bunch of choices, and you select one of them. So effectively, you just type the entire 8 or 9 letter word using just 4 taps, right, or 4 keystrokes. And so I think we run into the same problems, right? We may be able to detect those 4 initial letters that you typed and then use some kind of prediction framework on top of it to predict those those auto completed words, if you may. But absolutely, now can we predict whether someone typed an autocorrect or tapped chose the autocorrect option? Well, no. Right? So effectively, from our framework's perspective, that would just boil down to a 4-word letter. Now, when we were doing this work, actually, our focus was more on at least at the beginning, was more on the numeric keypad. And we wanted to, and numeric keypads are used by people a lot of times to type, PIN codes or basically phone numbers, etc., which are very difficult to autocorrect. So there is really not a lot of autocorrect that exists, right? So at least those frameworks are not impacted by that. But you're right, Amanda. Did I don't know, even answer your question?
No, absolutely. That's my only thought was trying to integrate some of those same predictive mechanisms back into trying to understand what they're typing. So that makes a lot of sense. It's a very difficult problem.
Absolutely. That is where our research stopped. We did not, and we mentioned that in our paper, that especially the second scenario that I talked about, that yes, if you have some kind of a prediction mechanism which is going to take the outcome or output of this model and then do a better job, yes, you are going to get a better accuracy overall.
Thank you, Amanda. Murtuza, I'm going to read a question for one of the attendees that doesn't have access to a microphone. It's about your lock work. And it basically asks whether you've considered the scenario where someone is in the process of entering a combination and they're entering an incorrect value and they start over.
So yes and no. So basically, the reason why I said no is we didn't explicitly evaluate those scenarios in our framework. But I think the way you can correct it is, and the work that I've not talked about over here today is we designed actually, unlocking detection mechanism. So effectively what we try to do is we try to detect something called spins, right? So if you are unlocking your lock, you do these motions, right? So these are called spins, right? And what we try to detect was we try to detect these spins, and based on the number of spins that we detect, we predicted it to be an unlocking operation or not an unlocking operation. And then our segmentation algorithm was also observing the energies that the basically gyroscope was giving us to kind of separate out, right? Where is the first phase ending and the second phase starting, right? Now, what will happen is if someone messed up, right? Obviously, we'll be able to predict that someone messed up and typing again, right? We will definitely be able to detect that. Whether we'll be able to correct is something that we have not tried. But does that answer your question? Or I hope yes.
Yeah, I'll be watching the chat, but yeah, I think so. Yeah. So I guess the last couple of questions are kind of at a higher level. Let me scroll back up and get to this. Here we go. So basically, this is a question from Mimi, and it asks, are there any existing techniques that could be used to protect the devices from your attacks? So we know the problem, but how do you solve it?
Yes, so let me, I don't know if I may take up a few minutes. Let me present some slides which I already had for that. I don't know if you can see my slides, right? Right.
Yep, looks good.
Okay, so to answer the question, how do you protect against such attacks? Well, throw your watch away. The second thing is like me, right? Wear an analog watch. I actually have been working for the past 8 years, I think, in this area, and all my students have a smartwatch except me, right? So basically, do that, or obviously go over a much more, much more different perspective of protecting against. But effectively, like to get serious, there are two techniques, right? On-device mitigation or off-device mitigation, right? So on-device, effectively, what you're going to do is you're going to try to design an access control mechanism on when you should stop access to these sensors, right? And effectively, you cannot just constantly stop access to these sensors. You need to do it smartly, right? So let's say if you're trying to protect against typing, so when do you stop access to your motion sensors? When you detect typing, right? And we showed in our work, and I have not presented those results over here, that it is possible to detect with very high accuracy when someone is typing, right? And so you can use that to design a kind of an access control mechanism to prevent access to motion sensors to any applications or specific applications at that time, right? So that is one approach that you can do. The second approach is kind of an off-device mitigation approach, and several different techniques, right? So one could be keyboard randomization, right? So this is basically another work that we did where we randomized keyboards, and this focused on just numeric keyboards, and we tried different strategies, and actually we recruited a lot of participants. I think almost 100 participants to see how people use these kind of randomized keyboards, right? It was amazing actually, this work, where this was completely a usability work. And yes, people don't like to type on. So this is a difficult technique to actually implement in practice, right? But this could be one technique. The other technique is, let's say for the second attack, right? We were trying to, how do you protect against inference on an external keyboard? And so we designed a pretty cool system where basically, if you see the slides over here, we basically tagged these the original keyboard with some markers, and then we use an AR system to basically overlay a new randomized keyboard on top of that original keyboard. So effectively, the user who's typing is going to see a completely different keyboard than basically what would be seen by the adversary. And this protects against also visual eavesdropping effectively. And actually, we designed the system, we implemented it, and we also did a lot of usability studies on it, right? So you can implement techniques like this, right? So again, there is a lot of work that we have done on protection mechanisms, and you can have a look at that in our papers. But these are some of, again, these are not a comprehensive list, but potentially some of the lists, some of the things that you can do.
Excellent. Thank you so much. So I believe that's all the questions that we have today. So thank you very much, Murtuza, for your presentation. You did an excellent job. And thank you for everyone for attending. We'll have a seminar again next week at 11 a.m. And watch our Twitter as well as your email for that announcement. Thank you. Have a good weekend.
Thank you very much, everyone. And again, appreciate everyone for coming and taking time and coming to my talk. Thanks.